Alright, so in a previous video we discussed a few things about energy, so we're gonna continue that discussion and give you a few examples. So to recap a little bit, the concept of energy is important, very important in physics. Energy is a number, it's a scalar, as we say in science. That is a physical quantity that doesn't have a direction. The units of energy are joules. So to specify the energy of a system, of an object in general, we just give a number and we specify that the units are joules, and that's it. That's all that you need to specify the energy. You don't need to give the direction, as will be the case, for example, for force. So the energy, 5 joules, that's perfectly well specified. Now, there's different forms of energy, right? We have kinetic energy, was discussed before, energy of motion. We have potential energy, energy due to location of the object. We said that two common forms of potential energy are the potential energy due to gravity and the potential energy due to an elastic material such as a spring, and those are both potential energies. We also have thermal energy, which is the energy at the molecular level that all objects have because of the temperature. We have electromagnetic energy, the energy contained in electric and magnetic fields. We have many other forms of energy. We're not going to go in detail through all of them. The two main ones that we're going to discuss are kinetic and potential energy, which, as we're going to say, they together, added together, we call it the mechanical energy of the system. So the concept of energy is important, is useful, because energy is conserved. If energy wasn't conserved, we wouldn't bother to deal with this concept. So this is a crucial element in this chapter about energy, is to be able to use the concept of energy conservation. We're going to discuss some more details of how and when to use it. That's going to come later. For now, we're just going to say that in general, when we're solving problems, any problem that we're going to apply conservation of energy, we're always going to be saying that the energy at some initial moment is going to be equal to the energy at some later moment in time. E initial equals E final. So let me give you an idea of where the concept of conservation of energy might come from. And let's start with a very simple situation, which is free fall. Let's say that you drop an object. At some given moment in time, the object is coming down. It has a velocity v initial, and it is a height h sub I above the floor. And some later time, at a later time, the object has a final velocity, and it has a height h sub f. You know that you can solve this problem or relate, for example, the initial velocity with the final velocity and the difference in height through kinematics equations, because we know that in free fall the object has constant acceleration given by minus g, minus 9.8. So you know that kinematics equations can be used to analyze this situation. So we're going to start with this kinematics equation, the one that has the squares. V final square equals V initial square minus 2g delta h. And what we're going to do is just going to open up that delta h in terms of what it means. Remember that delta, anything, means anything at the final moment minus anything at the initial. So delta h means h final minus h initial. We're going to open up that parenthesis, and then we're going to collect all the terms that have final on one side of the equal sign, and everything that has a subindex initial, we're going to leave it on the other side. So we get that 1/2 of v final square plus gh final equals 1/2 of v initial square plus gh initial. Now the next thing that we're going to do is to multiply by the mass of the object that is falling here, and what we end up with is this equation that says that this quantity 1/2 of mv squared plus mgh, when we evaluate that quantity at the final moment, well, the number that we get, we're going to get a number out of that. The number that we get at the final moment for this quantity, 1/2 of mv squared plus mgh, is equal to the same quantity evaluated at the initial moment. So the sum of the 1/2 mv squared plus mgh, we're going to call that the mechanical energy. The symbol that we're going to use is E mech for mechanical. E mech equals the 1/2 of mv squared. We mentioned before that is what we call the kinetic energy, and the mgh term is what we call the gravitational potential energy. We're going to use the symbol U sub g for gravitational potential energy. So what this simple kinematics calculation is showing us is that at least for free fall, the sum of the kinetic and the potential energy of the falling object, the mechanical energy of the falling object, remains constant no matter at what time during the fall you evaluate that number. When you take a picture, you stop your movie of the falling object and you evaluate its height, and you put that into mgh, and you evaluate its velocity and you put it into 1/2 of mv squared. You add those two numbers. Whatever number you get, let's say that you get 10 joules, those 10 joules are going to be the same no matter when you measure, when you stop the movie and calculate the velocity and the position. When you plug those values of position and velocity into the equation 1/2 of mv squared plus mgh, you will get the same 10 joules that you got before. So that's what it means when we say that the energy is conserved. It means that the value of the energy does not change. It is the same at all times. Okay? So specifically in this problem with a free-falling object, we have that the mechanical energy, the sum of kinetic and potential, is constant. Okay? Again, this was obtained just using kinematics for this example. So mechanical energy is conserved during free fall. Now what about projectile motion, which, as you know, is kind of similar to free fall, except that we're throwing the object with some horizontal and vertical components of the velocity. So for that kind of object is called projectile motion. We're going to assume that there is no air drag. And for this kind of motion, turns out that if you evaluate the mechanical energy of the projectile at some given moment, that I'm labeling here initial, the mechanical energy at the initial moment, given by its kinetic energy plus its gravitational potential energy. And if we evaluate the mechanical energy at a different moment in time, later on, where the object is at location F, the mechanical energy 1/2 of mv final squared plus mgh final, turns out that they are the same. One more time, that number remains the same. As that projectile goes up and goes down, the mechanical energy is not changing a bit. It's exactly the same at any given moment in time. This, if you wanted to prove it, it would not be very difficult. Again, kinematics, you can use kinematics to prove that the vertical component of the velocity of the projectile satisfies that equation. And from that equation, it's easy to prove that the speed of the object at some final moment square is equal to the speed of the object at some initial moment square minus 2g times the difference in height between the initial and the final locations. And using that, it's pretty simple to figure out that the mechanical energy, one more time, would be the same. That the mechanical energy at that point equals the mechanical energy at that point. Again, that's what we mean when we say that the mechanical energy is conserved in projectile motion. All right, we have another situation here that we can analyze using kinematics. Not very difficult to analyze it using kinematics, and we're going to arrive to the same conclusion that we had in the previous two examples. I won't take you through the details. It's not very difficult, but I just want you to get the idea here. Again, if we have an object that we put on an incline, no friction, we just throw that object at the bottom of the incline. At some moment in time, the object has some position described by x sub I along the incline. Also, that position is related to its initial height, and the object has some velocity. As the block goes up the incline, some moment later it's going to have a different velocity, it's going to have a different position. Well, we can use kinematics to figure out how those quantities are related. How is the final velocity related to the initial velocity and the difference in height and so on. The analysis goes something like this. Again, I don't want to take you through all the details. Not very difficult to prove that, one more time, when we simplify things and use kinematics, we arrive to the same exact conclusion that we had before. In this kind of system, a block sliding up an incline, the mechanical energy, one more time, is the same at any given 2 points on that incline. The sum of the kinetic energy and the potential energy remains constant as the block is either going up the incline or sliding down the incline. As long as there is no friction, we have the mechanical energy being conserved throughout the motion. So again, mechanical energy at one point matches the mechanical energy at a different point. As long as the object, the initial and the final are moments in time where the object is doing its thing, nothing is interfering with the motion of the object, there's nobody pulling on the object, we just set the object in motion and we let it do whatever it's going to do. When we evaluate the mechanical energy at one point in time and we evaluate it again sometime later, we find that the number hasn't changed. So there seems to be this sort of magical number that we're calling at this point mechanical energy, the sum of the kinetic and the potential energies of an object, which seems to be, I say magical because for some reason it remains the same. As the object does whatever it's doing, the number, the mechanical energy, remains constant. So we can use this knowledge to calculate different things. Like I said, we could calculate this, at least for these examples that I described, these three examples that I discussed, you could use kinematics, but you're going to see here that using conservation of energy is faster. And on top of that, conservation of energy applies to situations where you cannot use the kinematic equations for constant acceleration. So you need to learn the concept of conservation of energy to solve many different kinds of problems. So let's use the concept of conservation of energy to solve this question. If we drop an object from rest, a height h above the ground, what is the velocity of the block right before it hits the ground? We're looking for the final velocity right before striking the ground. So the way to solve it using conservation of mechanical energy would be to say evaluate the mechanical energy at the top. We say mechanical energy is always kinetic plus potential. How much is the kinetic at the top? Well, at the top we say that the object was starting from rest, so the initial velocity is 0. So no kinetic energy, we have a 0 for kinetic energy. And the potential energy is simply mgh. We're calling that initial height, we're just calling it h. So the initial mechanical energy is mgh. The next thing that we do to solve these kind of problems is to evaluate the mechanical energy at the final moment, right before it hits the ground. How much is the mechanical energy? So the mechanical energy, always kinetic plus potential, 1/2 of mv final square plus mgh final. And now the thing that is 0 is actually the final height, because we're going to assume that the height when the ball gets to the floor, the height of the ball is 0. So the final mechanical energy is simply 1/2 of the mass times the final velocity squared. And since we learned that the mechanical energy in free fall is conserved, those two numbers must be equal to each other, which means mgh equals 1/2 of mv final square. Notice that the mass is on both sides of the equal sign, we can cancel it. And solving for the final velocity, we get square root of 2hg. So as you can see, setting up the problem is not very difficult at all. It saves you a few steps. If you did it with kinematics, you would add a few additional lines of equations to get to the final answer. And we get that the final velocity is the square root of 2he. Now let's solve a similar problem with the block sliding down an incline without friction. We're going to have the same block that we released before, but and we're going to put it at the same height above the ground as before, h. But instead of free falling, instead of falling straight down to the ground, the block is going to be forced to slide down that incline, but there is no friction. So we're again interested in finding what's the final velocity of the block. That is the velocity of the block when it reaches the bottom of the incline. So having proven that in this situation the mechanical energy is also constant, we can start from there and say what is the mechanical energy at the top. So if the object was at rest, we have 0 velocity initial, so the kinetic energy initial is 0, the potential energy is mgh, so our initial mechanical energy is mgh. We do the same thing that we did before, that is we evaluate the mechanical energy at the bottom. The kinetic energy is 1/2 of mv final square, and the potential energy is going to be 0 because the height of the block at the bottom is 0. So it's a 0 for mgh final, and we make initial mechanical energy equals mechanical energy at the end, which results in mgh equals 1/2 of mv final square You probably remember that this is exactly the same equation that we got before, and the final velocity is square root of 2hg. So we have gotten the same exact answer for the velocity of the block at the bottom. So in one situation we have free fall. We use conservation of mechanical energy, saying that the sum of kinetic and potential was constant. In the other situation where the forces acting were gravity and the normal force, we said that that was also a mechanical energy conservation problem, and we used the same exact equation, and the speed at the bottom we found it in both cases to be the same, square root of 2hg. So what is this telling us? Notice that the difference between these two situations is that in one case the object is only affected by gravity, and in the case of the inclined plane the block is affected by gravity and the normal force. Now, because the answer is the same, the analysis is exactly the same, we can conclude that the energy of the block is not affected by the normal force. The normal force affects the trajectory of the object, but it doesn't affect its energy. Okay? So in general, we're going to learn, when we discuss the concept of work, we're going to learn that only forces that have components parallel to the direction of motion can change the energy of an object. In other words, can do work on the object. Okay? Clearly, the normal force, by its own definition, is always perpendicular to the motion, so the normal does not have a component parallel to the motion, therefore it cannot affect the energy of the object. So if we take that to its most general conclusion, we'll have to say then that even when the incline is not straight, even in a situation where the track is sort of like a roller coaster track, even in a situation like this where the normal force is always going to be perpendicular to the track by definition of the normal force, then in this case, if we don't have friction, we need to conclude then that the normal force is not going to affect the energy of the roller coaster cart, and that in the absence of friction, the mechanical energy of the cart is going to be kinetic plus potential, and it will be the same before and after, and therefore we expect that that mechanical energy is conserved for a roller coaster situation, provided there's no friction. So we could solve a problem of a roller coaster cart. Say that the car starts at a height h above the ground from rest, let's say, and if the question was what's the velocity of the car at the bottom of the track, we already know that this problem, because the idea of conservation of mechanical energy applies to this situation, we're going to get to the same answer that we've been getting in the last three examples. That is, the final velocity is going to be the square root of 2hg due to conservation of mechanical energy. All right, so that's all I have for now. I'll see you in the next video.